Hello, I'm Shunsuke Nozaki, a master student at ELSI Tokyo Tech. It is a great honor to be able to speak to you today. I'd like to thank the organizers for choosing my abstract for live streaming. Today, I'll give you a presentation of the results of high-pressure viscosity measurements of MgSO4 solutions, which is one of the possible compositions of the subsurface ocean of icy satellites, and some implications for these environments and habitability. First, I would like to introduce icy satellites. Icy satellites are the major type of satellites of outer solar system planets and are composed mainly of ice and rocks. With the research progress, it has become highly probable that some big icy satellites such as Ganymede, Europa, and Titan have an ocean of liquid water underneath the thick ice crust covering the surface. Understanding this ocean environment is an important topic because it can lead to discussions on the diversity, material cycle, evolution, and habitability of icy satellites. What is the ocean environment like? This figure is the pressure and temperature phase diagram of pure water. Markers on the vertical axis indicates the pressure of the boundary between the hydrosphere and the rocky layer of each body, Earth, Europa, Titan, and Ganymede. As you can see here, the ocean on these icy satellites has a larger maximum pressure than the Earth's ocean and reaches 1 gigapascal in some satellites. The assumed pressure-temperature conditions inside the icy satellites are shaded in blue, and conditions of the ocean are shaded in red. It should be noted that the actual ocean contains a variety of salt, which lower the melting point somewhat and broaden the condition of the ocean. The composition of the ocean has been discussed from various viewpoints, such as surface composition. In this study, we focus on MgSO4 magnesium sulfate as one of the possible compositions. For a more accurate view of the ocean environment, it is essential to understand how the ocean fluid behaves under low temperature and high pressure. Here, I will focus on viscosity as one of the essential properties of the fluid. This property determines material transport by diffusion and how fluid moves. Viscosity is dependent on pressure, temperature, and composition. The figure shows the change in viscosity by adding various salts to water, where the horizontal axis is the concentration, and the vertical axis is the relative viscosity to water. In particular, the effect of MgSO4 on viscosity is very large. In other words, if the subsurface ocean contains a lot of MgSO4, the viscosity of the ocean fluid may be completely different from the pure water ocean. However, there are no viscosity data under the temperature and pressure condition of the ocean. Therefore, this study aims to determine the temperature and pressure dependence of viscosity of aqueous MgSO4 solutions at low temperature and high pressure, which can be applied to icy satellites. In this study, the viscosity of a 10 weight% aqueous MgSO4 solution in these conditions was measured by the falling sphere method using a diamond anvil cell, a high-pressure generator, as shown here. The temperature was controlled by flowing hot and cold water through the duct, and the pressure was determined using the Ruby fluorescence method. The principle of the falling sphere method is simple. This method obtains a fluid viscosity by measuring the velocity of a falling sphere through the fluid. This working equation is derived by considering the balance of gravity, buoyancy, and viscous resistance on the falling sphere and the device correction factor. Here, gamma is the correction factor, A is the radius of the sphere, rho is the density of the sphere and fluid, respectively, and g is the gravitational acceleration, and v is the terminal velocity. To acquire the velocity of the falling sphere in the dark, I constructed this system. This is a simplified image of the system, and this is a picture of the dark diamond anvil cell used in the experiment, and a photo inside the cell. The diamond anvil cell is mounted on a rotating stage, and each rotation of the stage brings the sphere from the bottom to the top of the sample chamber. Then it can be dropped. Using light, microscope, and camera, I monitored and recorded the drop motion. Then I measured the velocity of the sphere and calculated the viscosity. Let's move on to the results. The plots on the left figure show the experimental results, viscosity of magnesium sulfate solution at all 7 temperatures. The values at atmospheric pressure are from the reference. The viscosity value acquired ranged from 1 to 10 millipascal seconds. On the right figure, the viscosity of pure water is shown as a dashed line for comparison, and the viscosity of various aqueous electrolyte solutions by reference is shown as a dotted line. As with the viscosity of other aqueous electrolyte solutions, the pressure dependence of the viscosity of magnesium sulfate solution can be fitted by the quadratic equation shown by the solid line. At all temperatures, the viscosity of magnesium sulfate solution is much higher than that of pure water. Using the pressure and temperature dependence of viscosity obtained in this study, I calculated the viscosity at a given temperature and pressure. I drew isoviscosity lines on the phase diagram of 10% magnesium sulfate solution. The shaded area represents the temperature and pressure range of the subsurface ocean, while the viscosity of pure water ocean, shown in the right figure, is around 1 or 2 millipascal seconds. The ocean of 10% MgSO4 solutions can vary from 1 to 10 millipascal seconds, one digit variation depending on the condition. I showed that viscosity of subsurface ocean fluid may be highly variable, one digit in the case of 10% MgSO4 solutions. So I will introduce some implications for IC satellites. This is the simplified cross-section illustration of IC satellites with some possible phenomena related to viscosity and habitability. Viscosity relates to how ocean fluid moves. It affects the convection style of the subsurface ocean and fluid movement velocity through rocks and ices. Therefore, the timescale of differentiation of these bodies and water circulation. From an astrobiological point of view, diffusion is one of the important keywords related to viscosity. The diffusion coefficient in a solution can be written as the Stokes-Einstein equation, which says the diffusion coefficient is inversely proportional to the viscosity. Therefore, viscosity variation affects the efficiency of material transport by diffusion and reaction related to diffusion for the life process, such as nutrient transportation. Let's move on to the protein. As you know, proteins are large molecules and are composed of long chains of amino acids. In a solution, proteins have variable structures. In proteins, processes such as folding and catalysis slowed by solution viscosity around the protein, because a protein must move in a viscous solution. Now let me touch on the implication based on the study of the prebiotic chemistry on the Earth. When a double strand, like DNA, diffuses apart, high viscosity makes it difficult for these strands to rebind again, allowing small oligonucleotides to bind each strand for replication. Although this study assumes much higher solvent viscosity than measured in my study, and its discussion includes temperature increase and decrease cycle, this has an implication for the possible biological process under the high viscosity condition of the subsurface ocean. In summary, viscosity variation of the subsurface ocean fluid, 1 digit in the case of 10 weight percent MgSO4 solutions, occur due to pressure, temperature, and concentration change, which might affect convection, differentiation, chemical evolution, and habitability. This is the summary slide. Thank you for listening.